GM, and welcome to the Rollup. Today's episode is with Liesl and Simon from Essential, the first declarative blockchain. Declarative programming has been around for quite a long time, and it's where developers will express their intent, and there's a process of solvers trying to fulfill that intent with background processes. In blockchain, it's very similar, except that users express their intent, and there's a network of solvers that will fulfill this intent on-chain. Essential takes this declarative nature all the way down to the most fundamental level, where validators will solve the next state of the blockchain. In Essential and declarative blockchains in general, there is no execution, and that's something that makes Essential very special. We talk about all of this and more on today's podcast. Before we get into it, here's a word from our sponsors that help make all of this possible. Enjoy. Cartesia is your home for app-specific rollups. At the forefront of developing new tools and platforms that enhance the capabilities of blockchain technology, Cartesia enables applications that are flexible and built to scale. Build on a full Linux environment and use traditional software libraries, but in blockchain development. Go to cartesia.io, that's cartesia.io, to learn more about building your own app chain today. Welcome to the Rollup, everyone. We are back today talking about declarative blockchains and intents. This is a new paradigm. We're making the transition from imperative to declarative. We're going to talk all about what that means, the declarative nature of blockchain transactions and intents. I am here with Liesl and Simon from Essential Intents, and very excited to dive into what you guys are building and everything going on in this world of declarative blockchains. So thanks all for coming.
Yeah, thanks for having us.
Yeah, thank you.
Awesome. Well, I think the word here that is kind of profound that we haven't heard so much in the blockchain space is this declarative word. And so I'm curious, like, where does this come from? And then we'll get into kind of like how you guys use this in blockchain transactions.
Sure. Yeah. The declarative imperative sort of comparison is one that's existed in computer science as a concept for quite a while. And basically, on a fundamental level, you have imperative programming and declarative programming, which are different ways of approaching like how we build computer programs. So imperative programs are focused on how to achieve or how to execute something by sort of executing specific instructions. And declarative programming focuses instead on what the program should accomplish rather than how it should. And so when you sort of apply those concepts to a blockchain context, it becomes pretty clear that expressing an interaction with a blockchain in a declarative way, saying what you want to accomplish rather than how, is a lot more ergonomic and intuitive on the user end and also on the sort of entire infrastructure layer. So we're building what we call the first declarative blockchain, which really applies this idea of, how do you describe what and how do you enshrine what you want an outcome to be on chain, and ensure that gets preserved all the way throughout the transaction supply chain, so that no matter what the conditions are on the chain or any actors that are standing in the middle, that users are always guaranteed the outcomes that they asked for, and are also sort of statistically or probabilistically guaranteed the best possible outcome that can be achieved on chain at that time.
It's awesome. I recently heard that this could be a potential application of ZK technology where you have some sort of like intent, and then the ZK verifier is actually proving that you got the best execution possible in that, given some constraints like timing. And so I found that a very fascinating use case for ZK, like provable execution. Found that really cool, because payment for order flow and all this like toxic order flow, toxic MEV, toxic execution has really plagued both the off-chain and the on-chain world of just going back for a long time. So I found that really cool. Okay, so you mentioned like declarative in general is this ergonomic switch to saying like, hey, I don't really care how this thing gets done. I just want this thing done. And so when we're applying that to the current blockchain landscape today, I think when we initiate a transaction, really on any L1 or L2, this has all been done in this imperative nature. Like I instruct you, do the transaction, make an approval, make a swap. But now we're kind of doing this paradigm shift. So what's the rationale for this declarative in a blockchain sense? And how do intents? What's the rationale behind intents, and how do we incorporate intents in the declarative nature of blockchain transactions?
All right, yeah, I was going to say intents are sort of a concept that like enshrines this declarative nature of what can be achieved with interacting with blockchains. So they're very much about expressing what you want to happen and sort of outsourcing the how. And so in the case of the sort of first generation of intent projects, it's up to solvers to discover how to achieve that outcome by sort of exploring the on-chain solution space, but then providing a solution in the form of a transaction, which then still goes on into the sort of like MEV dark forest, and has all of this additional execution risk between what the solver provides and what the user might actually get on chain. So the idea behind intents is obviously letting users and applications describe things in terms of outcomes. But the next step in that is to actually enshrine those outcomes and ensure that a state update is only valid if the outcome is achieved. And there's sort of two levels to that. The first is just like baseline satisfaction that the minimum viable outcome that a user expressed is achieved, but there's also this additional layer of optimality. So if you think of the solution space of what a user is willing to accept as an outcome, there's like the worst case scenario that they will accept, and in most existing blockchain systems, that is what the user will get, because there's always someone who, if you set high slippage, is willing to sandwich you. And so this system that preserves the declarative nature all the way through the supply chain actually enables proof of optimality as well. So not only are you getting like the minimum thing that you actually expressed that you're willing to accept, but there's a competitive game that gives you the best possible solution.
Awesome. Okay. Very, very cool. Like how does this work? I mean, we've really traced through like the modular stack and like very, very many episodes here on the roll up, talked about, execution, consensus and DA, all the way through to settlement. Is a declarative blockchain structured in a similar way, or is it not? Like, what are some of the mechanisms that you change to achieve this declarative nature all the way through to settlement?
So I tend to appeal to kind of like a first principles kind of thinking way to kind of get my head around this. And so if you go all the way sort of back to, why do we have blockchains at all in the first place? It's because we have a sort of a large network of actors who need to reach consensus over state, and they need to reach consensus over what constitutes like a valid state transition. So to date, the way we've done that is we specify some virtual machine over which everybody agrees, exactly how this machine is specified, such that when I execute like a transaction, or I execute, I spin up an instance of this virtual machine for a given set of inputs, we all agree on what the output is. And that's only one way that works, and it's got us quite a long way. But fundamentally, like thinking back to, the fact that what we ultimately need to agree on is state and what valid state updates look like, that sounds like a very like declarative problem statement when you put it that way. And so we kind of started thinking, and we'd seen projects that were working in the intent space applying these principles to the way the user expresses what they want at a given time. And we realized that actually, what if rather than the output to that being a solver finds an optimal transaction, an optimal input to this virtual machine's state transition function, and instead just discovers like, what is an optimal state update that I could make? So then you have to say, okay, well, we can't have solvers just making arbitrary state updates. Like they just give themselves and all of their friends like arbitrarily large amounts of money. That doesn't work. And so we started thinking about how can I design applications that themselves are declarative. So any smart contract that I write, it needs to be able to define the ways in which its state can be updated. Like it needs that control over its own state. And that's where we got to thinking, well, maybe instead of having like a set of instructions written in some virtual machine that govern that, what if it could just express those rules as constraints that say, actually, if anybody can set my state to anything they like, but these are the declarative rules, the constraints that have to be satisfied for any solution. And sort of once you make that kind of shift in your thinking, you realize that actually I don't need like an execution virtual machine at all, because as long as that application can reason about the ways in which its state can be updated using constraints, which we posit that in all cases it can be, then you actually don't need this execution at all. You push that discovery of the next state off chain to a network of agents. They could be solvers, and then all you have to do on chain is check that for this new state, are the constraints all satisfied, and that has some really nice properties around scaling and things like that we can get into later, I expect.
Yeah. Before we do, we most certainly will kind of talk about like the impact that it has on scalability, and sort of the other optimizations that blockchains tend to optimize for security and whatnot. Before we get into that, I'm curious about the solver layer, because this is an inherent like piece of infrastructure that is very important to fulfilling these intents and these declarations. And so, like, how are you viewing the current landscape of solvers that are operating on the networks now? Are these sufficient? Like, if we totally adopt this declarative blockchain and we have a very significant throughput of intents that are going through the system, is the current landscape of solvers sufficient to fill all of these intents? And that's kind of a specific question, but I am just generally curious about the perspective. Like, where are we at? What is the state of this solver landscape now? Navigating multiple blockchains can be complex and cumbersome. Let's say you want to deposit into a lending market on Polygon because they have the best rates, but you only have funds on Optimism. So you bridge your funds to Polygon only to realize that you need Matic to pay for gas. Maybe you use a centralized exchange, or you ask a friend to pay for the gas, but only then can you finish your transaction. In a chain abstracted future powered by Connext, this is not the situation. You can connect your wallet to any dApp from any chain with all the complexities of swapping, bridging, and depositing, all completely abstracted behind the scenes. Head over to connext.network, that's connext.network, to learn more about Connext's Chain Abstraction Toolkit.
I think we're used to thinking about solvers in the context of sort of enshrined searches, and I think that's really where this paradigm came from. Was around we had MEV, and we had all of these searches dedicating a large amount of compute to working out how to extract value from the system. And so the initial intuition was, well, maybe we can turn this sort of searcher network into a kind of a solver network where they can contribute utility to the system. That's definitely, I think, is definitely part of any declarative system. This off-chain agent that discovers optimal solutions. I think an important kind of distinction to make is that there are certainly use cases where having specialized off-chain compute, like that can be searchers that have an awareness of great of a varied set of liquidity that they can tap into. They know about a great number of on-chain venues that they can use, and that sort of, I guess, that kind of elite competitive view that we have of solvers today. We think of things like CalSwap solvers and that sort of thing. That's certainly one aspect. We anticipate that in a fully general purpose blockchain, not all use cases will necessarily warrant like deferring to such a network. But I think that what's an interesting kind of distinction to make is when we talk about solvers in the general case, we're talking about any like off-chain compute in service of finding optimal solutions. So one example of this is, like, let's say I have some relatively large complex application, which I've managed to distill down like into a small-ish set of like constraints and invariants that I can express declaratively on chain. How I go about off-chain, like modeling what constitutes a valid state update, it may be trivial, it may not be. But the important distinction is that part is happening off-chain. So you can almost imagine a situation where an application, it can leverage like a competitive solver network to assist in finding these solutions, but if I'm an application developer and I write like a new application that has this large off-chain component, which I need to help me find some more solutions, that's something I can run myself. For example, I could run like almost like we see in like Web 2, if you have typical like client-side, server-side kind of application architecture, you can almost mirror that in Web 3 by having, what we're calling solvers in the general case be this off-chain compute. Like I could just run a server that knows my application very well and knows good techniques for discovering optimal outcomes. And then because the constraints are being verified on-chain, I still benefit from the sort of decentralized aspect of my application. So I think that's an important distinction to make when we're talking about solvers, like in the general case, is that we do encompass this sort of highly competitive, highly specialized solver network, the way that you would think about it in terms of things like CalSwap and Uniswap X and that kind of thing. But it sort of goes beyond that. It's really this idea of general off-chain compute being able to produce solutions which are then very, very fast and cheap to verify on-chain.
Awesome. Yeah, it's this idea of like have your cake and eat it too, or build it too, because you want this like very robust network of solvers that are able to fulfill these intents. And who better to know your application needs better than yourself? And so it only makes sense that you would build out that solver yourself. And then this is where kind of like the advantage of open source technology comes in, or maybe you do choose to open source that first solver that you build yourself to satisfy that application's needs. And then you open source that and you say, hey, if you can come build a better solver, come in, because it'll end up benefiting the other side of the coin, where it'll end up benefiting that application even more so than that initial iteration. So speaking of cake, there's like this standard that's out there now. It's this cake framework. Frontier Research put this out. It seemed to get some adoption. I think it's still like rather early or new in terms of the research that's been done with it. But I haven't looked into it too much. I'm curious, like being so deep in the intent space, what is your general perspective on this cake framework? Maybe helpful for our audience. Just what is it? And then we can talk about like how some of these projects are starting to incorporate it into their designs.
Yeah, so the cake framework itself is it's sort of like a working group to achieve some sort of standardization around how we as an ecosystem achieve chain abstraction with intents. So I think it's helpful to conceptualize of intents not as a use case in and of themselves, but as a primitive. And that primitive is applied in a bunch of different areas. So the sort of first generation of intent projects like CalSwap were applying it to swaps in a single chain environment. And then there's this other direction, which is applying intent to the problem of bridging, and more specifically, abstracting away the user interaction with bridges and enabling like actions across different chains without users having to directly express some kind of interaction with a particular bridge. So we've been working pretty closely with the people working on the cake framework, and looking at how do we as a sort of sector of the ecosystem take this idea of intents and apply it to a cross-chain environment and make sure that there is a degree of standardization. So what we're doing at Essential is slightly different in that we're applying the intent primitive to the design of a blockchain state machine itself. Like how do you design a blockchain that fundamentally incorporates this like constraint-based intent-centric model. And so that is quite different from the ecosystem that Cake cohort are building in. But there is a lot of overlap, especially in terms of how we build UIs that enable users to interact with intent-centric systems, how we build some kind of universal intent expression format that any solver in any ecosystem, whether it's solvers on Essential or solvers in any of the projects working in the Cake environment, that anyone can ingest an intent from anywhere and understand it because it's written with the same standards in the same language. So that's actually something that we're contributing to in the form of our sort of universal intent expression language called Pint for programmable intents, and it's primarily developed to express intents and express constraints in order to build applications on our chain. But at the same time, it's also, pretty universal and generalizable to any intent system. So if you imagine this future ecosystem where every user is interacting with a UI and a wallet and, solver networks that are fully intent-centric, it can sort of be like the underpinning that ties all of those ecosystems together.
Very cool. It makes a lot of sense that when we start to change the way that we're interacting with blockchains, it means that some of the infrastructure underneath is going to change as well. Calls for new standards. Pint, of which is one of those. The Cake framework. I also saw another standard, I think, put on by Across and Uniswap. That was this new ERC, and it was this idea of combining their solver networks so that the solvers could kind of watch this like common intent mempool, and just kind of like look at a common place to fulfill those intents. I'm curious if that is like, what do we expect that this is kind of like the end game where we're trying to kind of like plug and combine all of these intent initialization engines into one single mempool, almost like a global mempool of intents, and then have like a global liquidity layer that is also trying to fulfill those intents. Do you anticipate that we'll end up integrating a lot of these networks together, or is there certain reasons why they may or may not coexist?
I think integration is a lot of people's end goal. I think having a single, intent mempool where every single blockchain, interaction on every single chain goes through has some, scary implications for centralization. So I don't think it would ever fully get to that point. But yeah, definitely like a good example is if you see like intent order flow on Ethereum going pretty evenly split between CowSwap, 1inch Fusion, and Uniswap X, where any of those intents, the whole principle of intents is to be able to expose yourself to, every single source of liquidity on chain and off chain, regardless of where you are. But because these projects are all using different methods for solving and different standards, that order flow has been fragmented again. And so, coincidences of once across two different users using two of these different, still intent platforms, and maybe even with the same solvers operating in both of them, can't necessarily get that same, exposure because the order flow is still like segmented. So I think that if we don't sort of come together as a sector of the industry and create some sort of standardization to the point where order flow is shared between different platforms and different protocols, then we are kind of just taking the current problem of fragmented order flow and liquidity up a layer, and it'll still be a resource that can be guarded and can be that value can be extracted from. So yeah, order flow being purely like sort of proprietary, I guess, is something that I think everybody in this space recognizes that we need to move away from, and is something that I think most projects in the intent space are like collaboratively working towards.
Yeah, that makes a lot of sense, and we spent a lot of time really trying to think through like how we can create solutions that are not recreating the same problems that we have in TradFi, proprietary order flow, payment for order flow, that whole thing. So that makes a lot of sense. We want to try to solve these at a base layer, not just move them up the stack. And so I think some of these standards are really, really cool. It makes sense for some of these like very almost like similar, if it's both a trading engine and they expect kind of a similar style of intent where it's just swap here and here, or even cross-chain swaps, right? Just swap here, but on a different chain. Essential has like some much more general use cases as I'm coming to understand it, by providing solutions to intents of a much more general use case. You can provide just the state of the blockchain. It doesn't have to really have anything to do with value transfer, any kind of swap or bridge transaction. And so my question is, does this more general use case or more general intent call for a different kind of solver? or can you leverage kind of the existing solver networks that are out there now?
It's definitely got to be a combination of both. But I think existing solvers, like we have, great relationships with, and are doing like amazing work in the existing, in production intent solutions that are out there. But there is going to be a degree to which some more specialization is going to need to happen, and also some more like generalization. So certain solvers will, specialize in being general, and then sort of in the same way as searcher market dynamics currently work, there will be a long tail of opportunities where, it might not make sense for the largest solvers to be paying attention to various different corners of the chain, but that, there will be an edge for certain like more specialized solvers to fit in there. I think Simon also has some interesting thoughts on how solvers can fit into the network as market makers as well.
Yeah, I think that's like the real like power behind introducing the solver as like an abstraction is that a solver can be many things, right? Like it can be this kind of enshrined searcher that I mentioned before. It can be, a market maker who is able to provide solutions that are optimal, not because they're crunching numbers on like a million different exchanges and finding optimal routing, but just like they're present on a ton of exchanges and they have the know-how to like model the execution risk of like showing a price here and then being able to like hedge it at a later time, which is always going to be sort of, if somebody is prepared to take on that risk, you're always going to end up with like a superior execution than someone who must have atomicity right now. So there's that, and then I think there's a nice sort of, if you think of, you mentioned like general state transitions and not just necessarily DeFi. Like you can imagine some kind of state that I want to change, and maybe that's just like I want to make a transfer from me to somebody else. Like I know what the solution to that looks like. It doesn't take a great deal of calculation to work out that I need to, reduce my balance by 100 USDC and increment somebody else's balance by 100 USDC. But at least what you get from the solver layer at that point is like the gas abstraction side. So like I just have to say this is what I want. Maybe I'm prepared to pay like some fraction of a cent of USDC for that to happen, and that can be the extent of my sort of intent. I can specify almost all of I can almost fully constrain the final state that I want. I just leave a little bit of uncertainty that says, well, how much am I going to pay for this? And like so the solver network there kind of covers this like gas abstraction side as well. So I think in kind of like one fell swoop, you kind of unite all of these different actors that are definitely add value in a network, and you sort of put them under this kind of like umbrella of solver that introduces all these things at once.
Awesome. And yeah, that makes total sense. I mean, it seems to me that we can also drive down some gas costs in a way if we're adopting that mechanism where solvers are the ones pricing in the gas price. There's no reorg risk. There's no finality risk of just making a transfer on the same chain. And so the solvers aren't taking on much risk in order to execute that transaction. And so is it true that maybe executing transactions in this way would kind of commoditize the transaction fulfillment in such a way that it would drive down the cost to execute that transaction?
Yeah, I think an important thing to note is that framing it in terms of like executing a transaction is sometimes helpful because that's the usual mental model that people come in with. But what's actually happening is not execution, nor is it a transaction, in the sense that transactions describe a particular sort of they target a specific smart contract, for example, and they say, this is the operation or the operations that I would like to undertake, and it sort of predefines in advance like this imperative model of like what are the steps that are going to be taken to get from A to B, and so the sort of major difference in this declarative system is the there is no like execution of transactions in the sense that we usually think about it, and so the concept of gas, which fundamentally is about charging rent for taking up compute power of a blockchain network, doesn't have to be applied in the same way because we can move execution off chain in this system. There isn't a need to have to pay for the repetition of computation that needs to happen in order for validators to verify the chain.
Fuel achieves higher throughput by utilizing a novel UTXO-based approach that allows for parallelized execution. This design significantly accelerates transaction processing, which enables Fuel to handle vastly more transactions than non-parallelized systems. Thanks to advancements introduced by Fuel, Ethereum rollups are set to be more powerful than ever before. And Fuel is not just enhancing Ethereum rollups, it's redefining them, making them faster, more scalable, and more adaptable to meet the needs of modern applications and developers. Go to fuel.network, that's fuel.network, to learn how to build on the Rollup OS. And so in a declarative blockchain, we're not necessarily paying for block space. We're just paying for solvers to fulfill our intent.
So ultimately, right down at the core of it, there are state is being updated, databases are being written to, and constraints are being evaluated, and those things are being done with some redundancy, be not by a validator set or anybody who has an interest in tracking the network. And so you do have to reimburse the network for those costs. The distinction is, firstly, that's like an order of magnitude or orders of magnitude cheaper, because just evaluating Boolean constraints, like is this satisfied or not, is much cheaper, and can also be like almost infinitely partitioned out. Like if I need all the constraints to be true, I can sort of partition those any way I like, and I can have them validated in parallel by a large network, and I just have to take the intersection of all the results and check that it's still true. So that's like a very nice property. I forget there was another part to your question there.
It was mostly about like not paying for block space. Like it is a fundamentally different mental model that we have when thinking about a declarative blockchain. And so, some of these like normal concepts of something like block space is scarce are now not necessarily accurate in a declarative sense. And so gas abstraction is one of them, because we're not necessarily paying gas for execution. Now solvers are pricing in the fulfillment of updating the state, and what it would take for them to provide that next state. It does take some resources on their part. And so because they're expending some resources, it makes sense that the person who's expressing this declarative intent is going to pay some fee for that solver to fulfill this next state.
Yeah, that's right. So like the only entity that directly kind of reimburses the network, in the base asset of the network, let's say, is the solver, because they're paying for the inclusion of their solution, and then the any user who's reasoning about state, they're sort of paying. And we sort of mentioned gas abstraction, so they could be paying with a completely different asset. At the same time, they're paying for any level of solution discovery they need. So the extent to which their sort of intent is unconstrained, and that there's still some uncertainty about where exactly in the state space to land is something that they can pay the solver for if necessary. And then also, they reimburse the solver for this kind of inclusion cost. But crucially, that can be done like in any asset, so you get this gas abstraction property.
Got it. Okay. So we refer to it more as a inclusion cost in order to include that in the next state update. And then we did talk about, and we're getting to like the impact on scalability. I promise. Like we're gonna get there. But I am curious, because you brought up like the way that validations work and how there is still some redundancy of let's say a solver provides the next state update, they submit it to the network, and then that's broadcasted to validators that agree and come to consensus on that state. And so how is that kind of like a normal consensus in terms of like how does data availability and consensus work in terms of a declarative blockchain?
Yeah, so I would picture the fundamentally the consensus mechanism working the same as you would have seen on any sort of layer 2. The distinction being just that the work that each validator is required to do is significantly lower for any one interaction, because all they're doing is checking the constraints are satisfied, and they're just evaluating booleans rather than each validator having to execute in order a large set of transactions over some virtual machine. I just have, this is the new state that's been proposed, and I have to check that it's acceptable from the point of view of all the state that it touches. Yeah, in terms of like data availability, that's like another place where like I think the declarative approach like fits very nicely into kind of a like a modular design, in that really the thing that's making changes to the network are solutions, right? But solutions are formed from the observation of intents that users are making, and so the only requirement for the intents themselves are never land on chain as such. Like they merely instruct what solutions should look like. And so the only thing that's required of intents is that they be available in a data availability sense. And so it sort of fits nicely into that paradigm too.
Got it. And something that you said, that since there are no transactions that are getting executed in sequence, these validators don't have to validate that these transactions are done in the right order. Is there no sequencer? Is there no need for a sequencer on a declarative network?
So you still need to determine at any one time, like for a given capacity of the network, like which set of intents will be, or like which solutions will be included. So it's more like, instead of like, okay, these are the transactions and this is the order I'm going to execute them in, it's how do I arbitrate between, if I have a very large set of solutions, and some of them will be mutually exclusive because they may be competing over exactly the same state, and probably will be. That's really where the sequencing side comes in, is okay, well, how do I select which solution is optimal in this situation?
Yeah. So let's say I do try to double spend, right? That's like the classical example of trying to operate on the same state. Like, which one goes through, right? Like, how do solvers come to terms with two contradictory intents?
Yeah. So sorry, Simon. There's some cases where, for example, you can imagine two intents where users are trying to swap like from the same asset A to asset B, and solvers might provide solutions for both of those that both happen to touch, let's say, like it's an AMM, and try to pull from the same liquidity at the same price. Obviously, only one of those is going to be able to go through before the price moves. But so you can imagine that, like in this sort of rich solver ecosystem, for each of those intents, there is not only one solution that's sitting there waiting to be, to compete, to be included. And so the sort of there's a stage, after solvers have initially like provided and committed their solutions, where then there's a collaborative block building process where solvers come together and basically try and like append new solutions to, in an ordered list, and try and find the most optimal, and optimality here is measured in terms of like how close to maximum satisfaction, in terms of what the user has expressed in their intent, does this solution or series of solutions get. And ultimately the consensus rules dictate that the winning block, the one that's selected, is the one that provides the maximum like aggregate utility across like all of the intents. So there may be cases where it is 100% zero sum. There's only one pot left. It's an NFT, for example. There's not going to be like an alternative option, and ultimately only one of those users' intents is going to be able to, or solutions is going to be able to get included. But for the majority of cases, one of the big benefits of having a solver ecosystem is that users aren't necessarily having to compete for like just the same liquidity in a single pool, because solvers are able to dynamically find, okay, if this solution is if this state space is no longer available, rather than still pulling from that same pool, what's the next best solution that we can find across the entire network?
Got it. I love that idea of maximum satisfaction based on the constraints that a user expresses. So that makes a lot of sense. Okay, so like what is the impact here? Like, traditionally blockchains have been faced with this trilemma, trying to provide very fast. I'm going to use the word transactions, but I realize that's not a very apt term in when we're talking about declarative. But traditionally, blockchains have been trying to provide fast transactions, cheap transactions, and secure transactions. And collectively, this makes a robust, efficient blockchain. And so that's traditionally this trilemma. How does that, like, how do we just kind of like solve that with this declarative blockchain? What is the impact on scalability, on speed, cost, and security as a result of using a declarative programming in our blockchain?
So one example, well, I guess fundamentally the answer is that it's much, much cheaper to verify a set of constraints are satisfied for a given solution than it is to calculate that solution. That's sort of where the gain in sort of scaling, faster, cheaper transactions is coming from. I think a useful example to think about is like, let's say like a transaction that's executing a swap on some AMM, like on the EVM, for example, like you just have to sort of see the complexity of this operation. You just have to read like the smart contract, and you'll see, or even you can look at the assembly, and you'll see basically all of these operations that are happening, many of which are really just sort of setting up what turns out to be a constraint-based problem in the end, which is, in the namely, if you're dealing with a constant product market maker, you just have to check that the product of the liquidity before and after is the same modulo some fee. Whereas, if you just do that directly declaratively, all for a given swap, what a swap looks like from the point of view of a validator is this AMM has a new state now, like the reserves have changed. All I have to check as a validator is if I take the product before and after this solution, is it the same? And that's literally all the validator has to do to check that, okay, the state of this AMM has evolved in a way that is that satisfies the constraints. So kind of this whole overhead of of setting up the constraint problem is kind of factored out, and the off-chain solver can model the curve of the AMM imperatively if they choose to. Like they can use some functional methods to work out what should the reserves be before and after for a swap of a given size. But like once it lands on chain and the validator has to check, is this a fair swap or not? All I have to do is just look at the state before and after. And so hopefully that illustrates that it's a lot less load on the validator network and on anybody who wants to be able to verify the chain than it is in an imperative design.
Yeah, and that load can be shared amongst a bunch of different validators. So for people who sort of understand in the modular ecosystem how data availability sampling works, you can do the same thing with sampling validity of constraints. So a bunch of different validators can collectively sample or validate pieces of these constraints and come together to sort of probabilistically prove that everything is valid.
Awesome. This has been a lot of fun. I feel like I learned a lot, and some of my most fundamental understandings of blockchains have been blown to bits. So thank you so much for coming on, and absolute pleasure learning about declarative blockchains.
Thank you so much for having us. Yeah, this was fun.
Yeah, cheers, Robbie. It was a good time.